Hello everyone, welcome to my lecture on Constraint Integer Programming and the CIP solver SCIP. I'm Leon, I work as a PhD student at the SUSE Institute as part of the SCIP group, and I hope you find something interesting in this lecture. I'll turn off my video now so you can focus better on the topic at hand, and I will see you at the end. Here you see a very basic outline of this lecture. During the first part, we will discuss constraint integer programming. We'll define what this problem class is and put it into contrast to mixed integer programming. Then we will spend the rest of the lecture discussing how to solve constraint integer programs. We will go through the design philosophy behind the constraint integer programming solver SCIP, and then in the latter part of the talk, we will discuss the solving concepts and strategies employed by SCIP. First, we define what a constraint integer program is, and then we look at an example to illustrate why this more general formulation might be useful. A constraint integer program has a linear objective function, and let me just point out that this is just a technical requirement. You can model any kind of objective function by modeling as a constraint and bound it by some variable and put this as the objective. The feasible set is described by an arbitrary set of constraints. So these can be linear or nonlinear, but they can also be more general, which we will see in the example later. The variable domains are either real or integer valued. And now the key restriction is that when all integer variables are fixed, the remaining subproblem is either an LP or an NLP. And we need this restriction because in constraint integer programming, we also want to do a branch and bound based solve, which is the same strategy that you would use in MIP. And this restriction is just the most general that you can find so that you get a relaxation that you can actually solve. And this is basically all you need in order to do your branch and bound solve. For an example, I like to look at the traveling salesman problem. Many of you will already know it, and even if you don't, it's very easy to understand. The problem is, given a complete graph with distances on all edges, to find a Hamiltonian cycle or tour of minimum length. On the right here you see the complete graph with 8 nodes, and I have marked a tour for you here in red. Let's look at a normal integer programming formulation for the TSP first. A straightforward way of modeling this is to introduce a binary variable for each edge, with the meaning that if the variable is 1, then the edge is in the tour, and if it's 0, then it isn't. Then we get this MIP here on the bottom. Let's go through the individual parts. Here we have node degree constraints. So for each node, we get one of these constraints with the meaning that for each node, exactly 2 adjacent edges have to be in the tour. But this alone is not enough to guarantee that you actually get a real tour, because the following can happen. You can get disjoint subtours. And to exclude these, you can introduce subtour elimination constraints. And the meaning here is, no matter which cut you take through the graph, you always need at least 2 edges in the tour traversing that cut. And this eliminates all subtours. The problem here is, of course, that there are exponentially many of these subtour elimination constraints, because you get one for each subset of the node set. And then the objective is, of course, to minimize the distance. Another type of constraint integer program is, of course, a mixed integer nonlinear program that we see here, where the constraints are general nonlinear functions. And you will hear more about this in a later lecture just on mixed integer nonlinear programming. To summarize and put it all into context, I have a little diagram for you here. So we start with MIP. Then as a subclass, we have satisfiability problems. A much larger problem class is mixed integer nonlinear programs. Even bigger, but where it's hard to find general purpose algorithms, we have constraint programming. And then right in the middle, we have the problem class that we are interested in, constraint integer programming. I invite you to pause the lecture here and answer for yourself these 2 questions. The first is, what is the key restriction that defines a CIP, and why is it necessary? And the second, think of a different problem that could benefit from a formulation as a CIP. So some problem class may be something that you are interested in, maybe something that you've heard of once before, but you know it's difficult to just write down as a MIP, something like this. And keep it in mind because this second part comes up again in a later question. The video will resume in roughly 10 seconds, and I will give a possible answer to both of these questions. For the first question, the answer is pretty clear. When all integer variables are fixed, the remaining problem is either an LP or an NLP. And it is necessary in order to be able to do branch and bound. We need to have a relaxation that we can solve. For the second question, there are of course many correct answers. I just put some possibilities here that you might have heard of before. First is the linear ordering problem. Could be useful for strainer tree problem, these kinds of things. You could also imagine a scheduling where you handle the time constraints through a constraint handler, and many more. We move on to the section where we talk about how to actually solve constraint integer programs. And this is of course what SCIP is for. SCIP stands for solving constraint integer programs. You will already have heard a bunch about SCIP in the past few days. And this next section, we discuss the whole design of a constraint-based optimization solver. The basic idea behind SCIP is that it's plugin based. So you have different plugin classes for different tasks. You can already see here, highlighted in blue, the constraint handlers, which are the most important plugin that we will also spend more time talking about throughout this lecture. But you have many other plugins such as presolvers, propagators, separators, and so on and so forth. As an illustration, here's a picture that we call the SCIP flower. So the whole gray part is the SCIP core that you see here in the middle. And then we have the individual plugin types. For example, on the bottom, we have the plugin type constraint handler. And then the most general and widely used one is probably the linear constraint handler, so linear constraints. But we also have, for example, the integral constraint handler that takes care of the fractional variables and the integral variables, and various other types. Or on the top, we have the reader plugin type, and then we have individual plugins for all the different file formats, such as LP, for example, or MPS. Let's expand on this a bit further. What is the SCIP core? So the SCIP core basically takes care of everything that a user does not have to worry about, and that you do not have to touch if you want to extend SCIP and customize it to your own needs. So for example, you have data structures for all the important stuff like the branching tree, all the variables, conflict analysis, the cut pool and cut selection and stuff like this, the click table. And then you have the plugins, which are external callback objects, and they interact with the framework through a very detailed interface. And the plugins are black boxes in a sense for the SCIP core, which means SCIP only knows for each plugin type the number of available plugins and the priority defining the calling order of these plugins. So SCIP doesn't know the structure behind any of these plugins. It will always just communicate with the plugin, give it some information, and ask for a return value. And this leads to a very flexible branch and bound-based search algorithm. Let us take a closer look at constraint handlers. Constraint handlers are the most powerful plugin type in SCIP, and they define the feasible region. We have already seen in the opening example of the TSP that a single constraint may represent a whole set of inequalities. So there we just had one no subtour constraint, and this takes care of all the subtour elimination inequalities that you might then add to strengthen your relaxation and enforce that you don't have any subtours. So the main functions of a constraint handler are to check and enforce feasibility of solutions. We will get to the difference between checking and enforcing a little bit later when we go through the SCIP solving loop. They can add linear representations to the LP relaxation. For example, let's say the subtour constraints. I mean, you can also add all of them in the beginning. This is sort of the standard MIP way, or you can add them dynamically later. For example, during constraint enforcement. They can have constraint-specific pre-solving, domain propagation or separation routines, but they do not have to necessarily have those things. But you can add them for your constraint handler if you know some additional information or have developed some additional technique. And as a result, SCIP is constraint-based, which is very flexible. You can add your own constraint type. It will integrate seamlessly with what is already there. And you can solve a wide variety of problems just by adding new constraint handlers. And the disadvantage is that you do not have a global view really anywhere. So a constraint knows its variables, but a variable does not know the constraint it appears in. This might seem confusing, but for some techniques, you would really want to have a column-based view on your whole problems. You can get this in SCIP, but it's a bit complicated and not that efficient, which is the reason, for example, why there has been this new addition of a separate pre-solving library, because in pre-solving you really want this global view to do column-based pre-solving. You have already seen on the picture of the SCIP flower that there are way more plugin types than just the constraint handler. And here we have a list of the most important ones. So separators just add cuts. So think of, for example, Montgomery cuts or mixed integer rounding cuts that you would just use to improve the dual bound. Pricers are for dynamic generation of variables if you're doing a column generation scheme. Heuristics, of course, find feasible solutions. Branching rules decide how to divide the problem. Then we have node selection, which subproblem should be regarded next. Pre-solvers, also very important to simplify the problem before starting the solve. Propagation routines, which simplify the problem and can improve the dual bound locally. Then we have readers, which we already saw in the SCIP flower. Event handlers catch events. They're also very useful sometimes for user extensions of SCIP. For example, if you want to do some calculation every time a new solution is found, you can implement this easily in an event handler that catches exactly this new solution event. Then you have display plugins where you can modify what SCIP displays as output. And a bit more rarely used are relaxation handlers where you can put in custom relaxations other than just the LP relaxation. You can see a lot of the information that SCIP has about its plugins just by running the interactive shell and using the display command. So if you, for example, type display branching, you will see a list of branching rules that are implemented in SCIP. So each line is an individual branching plugin. You see reliability pseudocost has the highest priority, so it will be called first by default. And the other ones will be then, if this should fail, the other ones would be called. Let's say we want to extend SCIP for our running example of the traveling salesman problem. Here we have, again, the SCIP flower, but instead of all the individual plugins, we have just summarized all of them as this default bubble. So what plugins would we need to add? Well, we definitely need the subtour constraint handler to dynamically separate these subtour elimination inequalities. We also definitely need a custom file reader because we want to just give the information of the graph and read this in and create our traveling salesman instance from this. We also might want some primal heuristics, for example, a two-opt heuristic that exchanges edges in the tours and tries to find better ones. And maybe we want to see how we improve while we're doing the solve. So see each solution that we found that was better than the last and how these tours change so that we can visualize it later. And for this, we might implement an event handler. If you would like, you could quickly stop the video here and find out for yourself what these heuristics do. Should only take you a couple of minutes. To summarize, plugins are black boxes for the SCIP core. They perform all problem-specific actions, and they interact with the SCIP core through a very detailed interface. The plugins can have private data. So, for example, in our TSP example, we might include a data structure for the whole graph in the subtool constraint handler. That might be beneficial to find the subtools. The plugins can access global information of the SCIP core, but, and this is important, they should not access data of other plugins. Because if the plugins would communicate directly with each other, this would destroy some of the flexibility of being able to freely add, disable, and enable different plugins without destroying the validity of the whole software. The result is that SCIP is constraint-based. It is easy to define new types of constraints and add them without having to worry about breaking anything else. And in this sense, it's easy to add problem-specific algorithms. Let's discuss some of the advantages and disadvantages of SCIP and constraint integer programming as an approach. So the first advantage is that it can be used as a black box MIP solver, although this is of course not an advantage singular to SCIP. You can use any MIP solver as a black box MIP solver. You have a lot of parameters to play with, hundreds of them in fact, so it is possible to customize SCIP to your own needs without actually implementing any code. SCIP is robust, fast, and well documented. It is, in my opinion, one of the better documented pieces of academic software out there. And you can extend it in any direction since it's constraint-based. So you can add problem-specific plugins and global constraints that can mean anything that you can imagine. Now, some of the disadvantages. You have hundreds of parameters to play with, which means it can be daunting to choose what parameter change might be useful for you. And the point that we already discussed, you do not have a global view on the whole problem matrix since the constraints are handled in the individual constraint handlers. We come towards the end of the second part of the lecture. And with that comes a second part of the quiz. So I invite you again to pause your video and answer these 3 questions for yourself. So first, just to recap, think of 3 different plugin types that you just learned about within SCIP. The second question is, why can't plugins directly communicate with each other? And the third goes back to your answer from part 1. So recall your own CIP formulation that you imagined from the first part of the quiz. What plugin types would you need to implement it? What could be useful and what could be needed? Once again, the video will resume in roughly 10 seconds with some answers. So for the first question, I have just put some examples here. You can also just go back to the video and look at the important plugin types. Why can't plugins communicate with each other? As I said, keep the framework as flexible as possible. If you have plugins that need to communicate with other plugins, then you lose the flexibility of just disabling plugins freely and enabling others. And for the last question, there is, of course, no correct answer. It depends on what you chose as your own CIP formulation. I just put some very likely candidates. So it's pretty likely that you need a constraint handler. It's pretty possible that you need a custom reader for your type of problem. And heuristics are always good. If you have some problem-specific knowledge in hand, then you can possibly devise an efficient, good heuristic that is not that hard to add. If you have finished answering the second part of the quiz, let's continue with the final part of the talk, the solving process of SCIP. So this part will be the most practical and also a bit more technical behind the scenes look of what is actually happening during a solve of a CIP inside SCIP. Let's first look a bit at the interactive shell. So the basic workflow, if you start SCIP just as a solver with the interactive shell, would be to read in your instance, let's say an MPS file, you optimize, then after you finished, you can write the solution out and quit. An interesting thing here is that you can use the display command, as you've already seen a few slides earlier, to obtain a lot of information about all kinds of things. And I invite you to pause the lecture here, start up SCIP, and just play around with the display command a bit and try to get an overview over the different plugins and things that you can find out. For example, you can display the table that you had before, or the different branching rules, but you can also find out what the default node selection rule is this way, or you can see all the different kinds of heuristics that are implemented in SCIP. In case you have never opened the SCIP interactive shell before, I'll show you how you can do it. It is not possible to do it from inside PySCIP opt, but you can still do it from this Jupyter notebook that is part of the CO at work. So I have it open here. And in the top right corner here, you see this new button. If you click on it, you can select new terminal, and it will open a new terminal. And then you can start the SCIP interactive shell by going to user bin and then SCIP. This is where SCIP is located, and if you enter it, SCIP will start up. And then you can use, for example, as I said, the display command. So as I said, please pause the video here, play around with this a little bit, and the lecture will resume in roughly 5 seconds. You can also use the set command to change settings, and you don't even have to change these individually. There are things called emphasis settings in SCIP, so you can, for example, set the emphasis of pre-solving to aggressive, and it will do more pre-solving and try to find more reductions than it usually would. And although I'm explaining these things from a SCIP shell point of view, because there it's easiest to display stuff, you can of course also change parameters in PySCIP opt by calling set param and then the parameter's name. Or you can also change emphasis settings, for example, for presolve by calling the set presolve function. Some generally important parameters that you should keep in mind when working with SCIP, or I guess any other MIP solver as well. The first important kind of parameter are numerical parameters. They have to be set in SCIP before reading a problem, otherwise it won't work. And there are 3 kinds. So there's the feasibility tolerance. The default is 10 to the minus 6. This tolerance means that, for example, when checking if an inequality is satisfied, a violation up to this value will still count as satisfied. Then there's the epsilon. Default value is 10 to the minus 9. And for example, values less than this epsilon will be considered as 0 in SCIP. So a value less than 10 to the minus 9 by default would be considered as 0. And then there's the infinity value. So any number higher than 10 to the 20 in SCIP per default will be considered as infinity. And you can expect, if you have values larger than that, or ranges larger than that, then you can expect numerical troubles to happen. Then there are several limit parameters that you can set if you do not want to solve forever and you only want to see how far you can get in, for example, an hour. Then you can set these. And if you want to do any kind of testing, then these randomization parameters are also very important. So you should, if you want to, let's say you developed an algorithm and you want to benchmark it, then you should definitely test it with various different random seed shifts to minimize performance variability. And then you can also change the random seed for the LP solver, and you can also change the permutation, which is mainly used in nonlinear programming. Let us talk a bit about different ways of using SCIP and interfaces. So the first possibility is to start the interactive shell and read in your problem through one of these 11 different input formats. The most commonly used ones are probably LP and MPS. Then you also already know Simple, the modeling language that is part of the SCIP optimization suite. The most complete way of calling any functionality is the C API and using SCIP as a callable library through C. There are also C++ wrapper classes. You have already been familiarized with PySkip opt, since it is the interface used in this CO at work, and also with the new Dockerized version of SCIP and the possibility to use SCIP as PySkip opt from a Jupyter notebook, which is very new. We're also planning a Conda integration that is hopefully coming very soon, where you can just use Conda install PySkip opt and then everything will be done for you. This is the goal. There are also interfaces to Java, Julia, Ample, GAMS, and MATLAB. If you keep with SCIP and you try to implement something, you try to create your own plugin, chances are you might get stuck at some point. And then it's important to remember this slide. And let me just mention that all the relevant links are down in the description of this video. So the first possibility is always to just type help in the interactive shell and a lot of information will be displayed for you. There's also extensive documentation online on the webpage. Not just the documentation of the code, but there is an FAQ, how-tos for each plugin type, and more useful information, for example, how to set up a debug solution. And you can also ask questions, of course. You can post a question on Stack Overflow using the SCIP tag, or you can write to the SCIP mailing list, which is very active and you will get an answer very soon. If you haven't done already and you plan on using SCIP, I highly recommend subscribing to the mailing list right now. We will move on with a more in-depth, behind-the-scenes look of the operational stages of SCIP. You see this flow diagram here. We will go into a bit more detail through the whole right part, where there's the whole main solving loop. Just let me note that a lot of these techniques should already be familiar to you from the previous lectures on the previous days, such as, let's say, pre-solving or LP solving. But feel free at any moment, if you're not familiar with a thing or you forgot what the main point is, to stop the video, go back to the previous lectures and refresh your memory. The first stage that you see here is the init phase. You don't have to worry about this too much as a user. It is where the basic data structures, for example the tree structure, are allocated and initialized. And it is also where you have to include all the plugins that you want to use. So this is mainly important for you if you want to write your own plugins, then you have to include them in the init phase. Next up, we have the problem specification phase. This is where the original problem instance is either read in by a file reader or created directly through the API. Or let's say you're using PySkip opt, then this is where you could create your model, either also reading it in through one of the file readers or adding variables and constraint until you have everything that you need. Next we come to the first phase, where you as a new user might start wondering what actually happens here. It's called the transformation stage. Here a working copy of the original problem is created. So it is important to understand that you can only change the original problem in the problem specification phase. Afterwards, when you go to the transformation stage, and I have a separate diagram for this here, all the original variables and constraints get copied to the transformed CIP, and all the pre-solving operations and other reductions only happen on the transformed CIP. This is useful because afterwards you know that, for example, due to pre-solving reductions, the model might have changed. In free transformation phase, you will actually check your final solution, transform it back to the original problem space and check if it is feasible there. So this is a safeguard of some sort. Pre-solving. By this point, you will have already heard some pre-solving techniques and ideas that you would usually use there. So I will not go into detail about additional pre-solving techniques, but instead I have some useful tips and parameters that you can use in SCIP for pre-solving. So first off, use display pre-solvers to list all the pre-solvers. So this display ... is always useful to get an overview, as I already mentioned before. If for some reason you want to disable all pre-solving for a model, then you can do this by setting the emphasis setting to off. This could be useful if you really want to know that the problem that gets solved is actually the problem that you put in. Maybe some research question, it is relevant. You can deactivate single pre-solvers, as you see on the deactivate single techniques point. You can set the emphasis setting to aggressive, so that it will try to use more pre-solving. And as a general rule of thumb, do only deactivate single pre-solving techniques if you encounter performance problems. In general, it is the ones that are enabled by default usually work pretty well and find reductions. And if you realize after doing some solves, oh, the probing takes forever and finds nothing, then you might consider disablement. We now come to the main solving loop, which consists of these 3 stages, but we will zoom in here a bit and take a closer look at what actually happens. This is the zoomed in view, and the way I will go about explaining this is that we will step through each of these main important steps during the solving loop and take a closer look. For many of these, I will not go into any explanation of what the techniques are, because they should already be familiar to you. For example, node selection or LP solving. If you feel like you need to brush up on your knowledge of this, feel free to stop the video at any time and go look back at the lectures of the previous days and what was explained there. What I will do is give some SCIP specific tips and important parameters for each of the components. So first we select a node. At the initial start of the node solving, this will just be the root node. And later on, when we have created multiple open nodes that have not been solved yet, we will select one of them. Here, again, you can display all the different node selection rules that are available to you. And the same as with the branching rules, only the node selector with the highest standard priority is active. So it is not that the estimate node selector happens twice as often as the BFS node selector, it will happen all the time. So if you set a node selection priority to the highest priority, then this node selector will be executed. After we have successfully selected a node that we want to solve, we go into the processing of that node. And again, here we zoom in a bit closer because a lot of different things happen. The first is that we do a round of domain propagation to hopefully make the problem a bit easier. And you might not actually be familiar with what domain propagation is, so I will give a quick example here and show you some of the goals. What you see here is a so-called all different constraint. This is more of a constraint programming kind of thing, but it is very easy to understand. So we have 4 variables denoted by x1 through x4, and they are all required to take different values. And on the left we see the current state, and what these red crosses are supposed to visualize is that x1 and x2 cannot take the red or the yellow values. For example, this could be because of some branching decisions. And then we can infer from this, and this kind of inference is called propagation, that because x1 and x2 cannot take the middle values, that x3 and x4 have to take the middle values and thus cannot take the green or the blue values. And so we get a domain reduction for these other variables. This was one example for a constraint-specific type of domain propagation. Generally, in domain propagation, the task is to simplify the model locally, or improve dual bounds, or even detect infeasibility possibly. Next up, we solve the LP relaxation. Let's look at some important tips and parameters here. So you can change the initial LP algorithm and the resolve LP algorithm in SCIP from Primal, dual, and barrier with and without crossover. So usually this will be the dual simplex algorithm, but you can change it if this is something that you want. You can choose what pricing method to take. Normally the specific default of the LP solver that you interface from SCIP is used. So for Soplex this would be DevX in most cases. And you can set the number of threads if the LP solver supports that kind of thing. Note that slow LP performance can be a blocker for the solving process because you solve so many LPs. And sometimes you can do a lot of things here manually that can improve your actual solving capabilities. In the case where we do branch and price, so column generation, where we dynamically generate variables instead of adding them all in the beginning, think of, for example, the cutting stock problem. We would do a round of pricing next, but this is not the topic of this lecture. So we go on to the cutting phase, so where we add linear inequalities to strengthen the LP relaxation, for example, Gomery cuts or Mir cuts. And I have another slide with important tips and parameters here. So you can set separating completely off, although this is for most things not desirable. The other two emphasis settings of fast or aggressive can make sense depending on your problem. If you experience that separating a lot just slows down your node processing, it doesn't really help anything, you might consider switching to fast. And if you realize that your trees get huge, you might consider setting the separating emphasis to aggressive and see if that helps. You can also disable signal separation techniques, same as with all the other plugins. And you can also change how many cuts are added, either at local nodes or at the root, always different, and how many rounds of separation take place. So you can fine-tune just with parameters how your separation, how much working limits you have. The next step on our journey through the solving loop is the constraint enforcement. And this might be new to you, and I'll go into a bit more detail because it is important. So constraint enforcement basically means that the LP solution may violate a constraint not contained in the relaxation, and therefore enforcing is necessary for a correct implementation. Let's go back to our running example of the TSP. What does constraint enforcement mean here? We do not add all the subtour violation inequalities to the LP because there are so many of them. So we want to dynamically add only those that are violated. And this is exactly what happens in enforcement. You can also add them during the separation phase, just to make your LP relaxation stronger. But at the end, after you solve your LP, you come to the enforcement step, you check, is there any violated subtour inequality in the enforcement callback of your subtour constraint handler? And if so, then you would add it at this point. So this is the idea with enforcement. And you see here on the bottom that constraint handlers can resolve this infeasibility by reducing a variable's domain, by separating a cutting plane, this is what we just saw, by adding a local constraint. You can create a branching. This is what usually happens in the integrality constraint handler. So you would check, is there an integer variable that has a fractional LP solution value? And if so, then you would branch. You can conclude that the subproblem is infeasible and can be cut off. This is good, then you are finished with this part of the tree. Or you can just say, solution infeasible, but I cannot resolve it. So here we have all these different outcomes again, and we will see what happens in the solving loop depending what outcome we get. So if we reduce the domain or add a constraint, then we go back to domain propagation and resolving the LP. If we added a cut, we directly go back to the LP. So this is sort of the difference between creating a local constraint and adding a cut. While with one we go back to do another round of propagation, and with the other we just solve the LP again. If we branched, then we are done with this node and can go back to select the next node. Cutoff, so infeasibility, and we know there can be no other nodes below this one, then we can go to conflict analysis, try to learn something from this, and then select the next node. And in case of feasible or infeasible, so for infeasible, the constraint handler will just say, no, this is no good, I cannot do anything anymore, and then usually if no other constraint handler can resolve the infeasibility, you would do a pseudo branching. And for feasible, you're also happy you're done, you can just select your next open node. And the last piece of the puzzle that we haven't looked at yet are heuristics. Of course, it can be very useful to find good solutions quickly in order to be able to prune nodes, but also just to have a good solution in hand if you don't finish yourself maybe. So let me again point out some of the important settings, similar to what you have seen before. You can change the emphasis setting for heuristics. You can enable or disable individual heuristics via the frequency, so frequency -1 is disabled. You can of course play around with the budget and the working limits of the individual heuristics. And as a general piece of advice, you should probably use the emphasis settings rather than tuning the individual heuristics by hand. The only possible exception to this is if you have a specific problem that you want to solve and you have found, for example, some problem-specific heuristics that work really well and are very fast, then you might consider disabling some of the more expensive heuristics in SCIPs because you might not need them. We're finished with this walkthrough through the SCIP solving process, so I have another final part of the quiz for you here. Please stop the video and answer these questions for yourself. Why does SCIP create the transform problem? What is the difference between enforcing and checking a solution? And during which stage do you have to include user-created plugins? Once more, the video will resume in about 10 seconds with some answers. As mentioned before, it is important to have the original problem still at hand without any changes, so that at the end of the solve you can look at your optimal solution, transform it back to the original problem, and see if it is actually feasible there. So this ensures feasibility. The difference between enforcing and checking a solution is that checking just checks if a possible solution is feasible or not, but it doesn't do anything about it if it isn't. And enforcing resolves infeasibility, and it is used mainly for the LP solution. And the last question, quite simple, it is the init stage. Before I end my lecture, let me point out some important topics and further reading if you want to get more into SCIP and constraint integer programming. So you can find more details, of course, in the online documentation. If you're interested in branch and price, you can extend SCIP to a problem-specific branch cut and price solver. There's a very useful Q&A on our YouTube channel. You might want to check out the bin packing example, and also, of course, GCG, the generic column generation framework. You can also do Bender's framework decomposition since version 6. There's also a Q&A that you might find useful on our YouTube channel if you have questions. And if you want to really get into the details of things, you can, of course, look at the technical reports on our webpage, where we have details for all the new and added features of SCIP. And with that, you have arrived at the end of this lecture. Thanks for paying attention. Thanks for sticking with me till the end. I hope you have learned something interesting, and I look very much forward to seeing you all in the live Q&A session. Bye.